Spring 1944, Wright Field, Ohio. Major G. Lundquist studied the flight test data from captured FW-190EB-104. The figures revealed a story that could save countless American lives if he could convince command of what he had found. For 2 years, this German fighter had terrorized Allied pilots across Europe. IAF squadrons spoke of a mysterious radial engine monster that surpassed their Spitfires in every aspect but one, turning radius. It was 60 miles per hour faster, rolled at 150 degrees per second, and carried 4 20mm cannons that could tear through a flying fortress in seconds. American test pilots approached the captured marvel with methodical precision. Lundquist strapped in, eager to uncover the secret of German engineering. His first flight seemed to confirm the legend: exceptional roll response, flawless ground handling, and terrifying firepower. But once they pushed beyond 400 miles per hour, everything changed. Elevator forces surged to unbearable levels. The A-frame shuddered violently, buffeted by invisible turbulence. Control became a physical battle with nature itself. The fighter that had ruled Europe's skies wasn't only fighting the Allies, it was fighting its own pilots. The Spitfire's Merlin engine sputtered twice before finding its familiar growl across the rain-slicked tarmac of IAF Pembrey. Flight Lieutenant Derek Ward pulled down his goggles and taxied toward the runway for another dull patrol over the Welsh coast, June 1942. Routine chatter filled the wireless, as sector control vectored fighters toward bogies that usually turn out friendly or imaginary. But Sergeant Bill Jeff, scanning the sky from the tower, lowered his binoculars, uneasy. The silhouette approaching from the southeast didn't match any friendly type. Too broad, too short. The nose gleamed with a reflection of polished metal, an unfamiliar radial engine cowling. As it banked closer, the black crosses on its wings became clear. "Christ almighty," Jeff muttered, snatching the field telephone. "Jerry's coming in to land." The German fighter touched down smoothly, its pilot seemingly unaware he had just handed Britain one of the greatest intelligence prizes of the war. Oberleutnant Armin Faber had been chasing a damaged Spitfire across the Bristol Channel when he lost his bearings. The Welsh coastline, from altitude, looked strikingly like France's. In the confusion of combat, even seasoned pilots could make fatal navigational errors. By the time he realized a mistake, it was too late to escape without being intercepted. Jeff ran across the field with a flare gun in hand, heart pounding. The Luftwaffe pilot was already cutting his engine, calm and resigned. Climbing onto the wing, Jeff met the gaze of a weary young officer whose pale eyes carried the fatigue of endless missions. Faber slowly raised his gloved hand from the control stick of what intelligence soon confirmed was a Focke-Wulf 190A3. For months, IAF Fighter Command had received alarming reports, encounters with an unknown German aircraft faster than anything in service, more agile than the Messerschmitt 109, and armed with weapons that annihilated bombers in seconds. Analysts first dismissed them as sightings of captured French planes, perhaps modified Curtiss P-36. The truth, however, was far worse. Germany had fielded a fighter superior to Britain's best. When Group Captain Hugh Wilson inspected Faber's plane at Farnborough, the grim reality came into focus. The FW-190 mounted 4 20mm cannons in its wings, dwarfing the Spitfire Mk VS-8 rifle-caliber guns. Its BMW 801 radial engine delivered 1,700 horsepower, giving it a speed edge of nearly 60 miles per hour. Most alarming was its roll rate, over 150 degrees per second, allowing maneuvers no Spitfire could match. The data painted a bleak picture for the air war over Europe. IAF pilots had been unknowingly facing an enemy whose aircraft outperformed theirs in nearly every respect. Yet, as British test pilot began flight trials, flaws began to surface. Wing Commander Humphrey Edwards-Jones reported unsettling vibrations at high speeds, crushing control pressures, and flight characteristics that made the aircraft demanding and exhausting to fly. The FW-190, it turned out, wasn't just a machine of dominance, it was a machine that pushed even its own pilots to the brink. Technologically advanced, the FW-190 demanded exceptional pilot skill to unlock its true potential. Flight test reports from Farnborough began documenting specific limitations that frontline intelligence had overlooked. Above 400 miles per hour indicated A-speed, elevator control grew increasingly heavy, requiring substantial physical effort to maintain combat attitude. The aircraft's superb roll rate came at the expense of greater pilot workload, demanding constant attention and precision with every control input. Most notably, the absence of rudder trim forced sustained pressure on the pedals, rapidly inducing fatigue in extended dogfights. These weren't fatal defects, but rather fractures in the illusion of flawless German engineering. British pilots soon realized that the FW-190's remarkable performance concealed deeper compromises in pilot-aircraft harmony. While the Spitfire had been designed to make an average pilot effective, the German fighter demanded extraordinary skill to reach its promised performance envelope. The difference wasn't purely technological. It was philosophical, reflecting opposing doctrines of air combat that would ultimately shape the war's outcome. As Faber's aircraft underwent deeper examination, British engineers began discerning patterns central to understanding German aviation philosophy. The FW-190 embodied ingenious answers to immediate tactical challenges, yet those same solutions introduced new complexities that Luftwaffe pilots had learned to endure through training and experience. The question now facing Allied air strategists was whether these weaknesses could be exploited in combat, and whether American pilots, with their distinct training methods and operational thinking, might identify vulnerabilities the British had missed. Major George E. Lundquist paced the edge of Wright Field Restricted Hangar Complex, his breath fogging in the crisp Ohio air of April 1944. Before him stood EB-104, a Focke-Wulf 190G3, recently arrived from Britain aboard a Liberty ship, carefully reassembled under tight security. At 8,535 pounds gross weight, loaded with ballast to simulate 550 rounds of 20mm ammunition, it represented the U.S. Army Air Force's most comprehensive captured fighter evaluation yet. With the invasion of Europe approaching, American P-47 Thunderbolts and P-51 Mustangs would soon clash with FW-190s in skies over France and Germany. Unlike the British, who needed fast tactical intelligence for immediate defense, the Americans had time for systematic, scientific analysis. Lundquist's mission wasn't merely to understand what made the German fighter formidable. It was to determine how U.S. pilots could defeat it consistently and decisively. Circling the aircraft's distinctive radial cowling, Lundquist studied the BMW 801 engine, its rugged build and advanced cooling system harnessing 1,750 brake horsepower. The four 20mm cannons mounted in the wing roots offered devastating firepower capable of shredding bombers in seconds, while the wide-track landing gear promised excellent stability on the ground. Everything about the FW-190's design reflected sharp tactical awareness and refined engineering logic. Early test flights confirmed British reports. Superb ground handling, smooth takeoffs and landings, and an intuitive single-lever engine control simplifying power management compared to the more complex systems of American fighters. Most striking was its roll performance. At 250 miles per hour, it achieved roll rates of 150 degrees per second, dwarfing the P-47's 90 to 100 degrees range. But as Lundquist pressed through increasingly aggressive flight profiles, the German fighter began to reveal its darker temperament. Beyond 400 miles per hour, elevator control stiffened alarmingly, requiring brute strength to hold formation or sustain high G turns. The A-frame began to buffet violently, vibrations rippling through controls and eroding precision. Captain Ray White, another test pilot on the program, compared notes afterward. He found that the lack of rudder trim demanded relentless pedal pressure, rapidly exhausting pilots during prolonged engagements. The elevator trim, though effective, operated too slowly to keep pace with rapid tactical shifts. Most troubling of all was the FW-190's abrupt stall behavior. It offered almost no warning before a sudden wing drop under hard turns. The American test team documented these findings with calm scientific rigor, not with the urgency of wartime defense that had characterized the RAF's earlier evaluations. IAF pilots had required immediate tactical insights, but the Americans had time to explore the FW-190's full performance envelope with scientific precision. This deliberate approach uncovered trends that combat intelligence had overlooked. The fighter's remarkable low-speed agility came at the cost of high-speed control stability, and its fearsome firepower demanded pilots accept significant handling compromises, issues that American design standards would never have permitted. Lundquist's detailed reports began to reveal a deeper truth about German engineering priorities. The FW-190 had been built for specific tactical conditions, the rapid strike-and-withdraw style of Luftwaffe hit-and-run attacks against Allied bombers. Its extraordinary roll rate and concentrated armament made it lethal in short, decisive bursts of combat, but prolonged engagements exposed weaknesses that German pilots had learned to master through training and discipline. This contrast became especially clear when American pilots tested the aircraft's turning abilities. Though the FW-190 could outturn AP-47 at lower speeds, its overall turn radius was inferior to more conventional fighters. The deployment of maneuvering flaps helped somewhat but couldn't overcome the core compromise between straight-line speed and sustained turning performance. German aviators had mastered using the aircraft's strengths, speed, roll, and firepower, while avoiding turning duels that revealed its flaws. American intelligence only gradually grasped this tactical adaptation. As spring shifted into summer and the D-Day invasion loomed, the Wright Field testing program expanded to multiple captured FW-190s. Each example told the same story: extraordinary isolated capabilities balanced by systemic limitations that German doctrine had learned to accommodate rather than eliminate. The Americans came to see that the dreaded FW-190 wasn't merely a better fighter. It embodied a wholly different vision of aerial warfare. Its implications extended beyond one aircraft's strengths or weaknesses. German design choices reflected strategic beliefs about combat that diverged sharply from Allied thinking. While German engineers optimized for pilot excellence and tactical precision, American manufacturers sought to make average pilots highly effective through intuitive control systems and forgiving handling. The FW-190 demanded elite skill to reach its full performance, whereas U.S. fighters were being built to amplify the pilot's natural abilities, not test them. This philosophical divide would prove more decisive than any raw performance figure. As Major Lundquist compiled his final analyses for European Theater Command, he was documenting more than technical data. He was charting two competing ideologies of flight. His findings would shape how the Allies approached air combat in the closing phase of the war. On a fog-bound October morning in 1944, a freight train from New York arrived at Wright Field carrying what intelligence officers called the most valuable captured aircraft of the European war. FE-121, a Focke-Wulf 190D, had been seized intact during Operation Bodenplatte. Unlike the battle-worn G3 Lundquist had tested earlier, this Dora represented the peak of German piston-engine fighter design, the Luftwaffe pride and propaganda claim, as the world's best combat aircraft. First Lieutenant Charles A. Russ approached the D-9 with the systematic thoroughness that defined American technical intelligence. While the British had prioritized immediate combat application and the Soviets focused on rugged practicality, the Americans aimed for complete, quantified data across the entire flight regime. Ross's objective was not only to understand the D-9's power, but to define precisely where that power began to fail. At first glance, the D-9 showed refinement, not revolution. Its stretched nose housed a Junkers Jumo 213 engine, over 1,800 horsepower, promising superior performance to earlier Anton models. The cockpit reflected the same German precision, clean instrument layout, logical control placement, and generally strong visibility except for the persistent forward blind spot from a long engine cowling. Ground trials confirmed the high-quality construction that had impressed evaluators since Faber's unplanned landing 2 years before. Ross's initial flights proved the Dora's formidable reputation. Climb rate surpassed the P-51 Mustang below 25,000 feet, and top speed neared 430 miles per hour at altitude. Its armament remained devastating. Two 13mm machine guns firing through a propeller hub, backed by two 20mm cannons in the wings. To Luftwaffe pilots trained to harness these traits, the D-9 stood as a pinnacle of piston-engine fighter evolution. Yet as Russ expanded the test envelope, the same inherent challenges that plagued earlier variants began to resurface. Fundamental limitations that had haunted earlier FW-190 variants reappeared in the D-9 with unsettling consistency. Beyond 400 miles per hour, control forces grew progressively heavier, demanding immense physical effort from the pilot to sustain combat maneuvering. The elevator buffeting Lundquist had reported in the G3 was even more pronounced here, confirming the flaw is systemic rather than isolated to specific aircraft or production runs. Captain Ray White, now the Army Air Force's most experienced captured aircraft pilot, conducted comparative trials against American fighters that exposed the full extent of the FW-190's operational weaknesses. Though the German machine excelled at lower speed with its exceptional roll rate and climb performance, high-speed engagements revealed vulnerabilities that U.S. doctrine could exploit. During simulated air combat above 325 miles per hour, the D-9's ailerons grew sluggish, while P-47 and P-51 pilots maintained precise control. Engineering analysis accompanying the tests traced these issues with alarming clarity. The FW-190's control system, built around pushrod linkages, gave superb responsiveness at low speeds but induced severe flutter under high G loads. American engineers identified the source of the aileron buffeting in the wing's torsional flexibility, optimized for roll performance at the cost of high-speed rigidity. The elevator problems, meanwhile, arose from aerodynamic design decisions prioritizing instant pitch response over stability during sustained, violent maneuvering. As more captured aircraft arrived through late 1944, the same flaws reappeared. An Anton 8 recovered from a crash showed identical control stiffness, while an F-8 variant from the Mediterranean theater displayed the same aerodynamic behavior, proving the issue stemmed from design philosophy, not manufacturing inconsistencies or battle damage. Ross cross-referenced American results with British and Soviet intelligence reports, discovering a pattern across Allied evaluations. IAF engineers had also identified these weaknesses but focused on exploiting them tactically, developing combat procedures to keep Spitfires and Hurricanes in speed regimes that favored British designs. Soviet test pilots took a harsher view. Their captured D-9s consistently lost mock engagements to La-5 fighters once dogfights extended beyond the initial attack phase. The tactical implications were unmistakable. German pilots had adapted their combat doctrine to align with the FW-190 strengths: swift strikes, quick disengagements, and minimal turning combat. Its devastating armament and rapid climb made it ideal for hit-and-run assaults on bomber formations, but unsuited for prolonged engagements where control precision mattered most. Luftwaffe training emphasized rigid tactical discipline to keep pilots within the aircraft's narrow performance envelope. American pilots, approaching the same machine with different instincts and training philosophies, immediately noticed features that German aviators had normalized. The absence of rudder trim, which Germans viewed as a minor inconvenience, was seen by Americans as a major ergonomic flaw increasing workload. Similarly, the slow-acting elevator trim system, acceptable in German doctrine emphasizing anticipation and preemptive control, struck U.S. pilots as a critical disadvantage in fast-changing combat conditions. These cultural and engineering contrasts illuminated deeper truths about each nation's approach to air warfare. German aviation embodied a philosophy built around elite skill, precision, and tactical excellence, machines designed for masters of the air. American aircraft, by contrast, were evolving into tools that expanded the capabilities of the average pilot, relying on ergonomic design, manageable control forces, and superior visibility. This divergence reflected broader strategic assumptions. Germany depended on a small core of elite pilots, while the United States leveraged mass training, industrial standardization, and aircraft that made competence more achievable. By the close of 1944, Allied air superiority over Europe was unassailable, and Ross's meticulous reports provided crucial insights to the air war's final months. The once-feared FW-190, long regarded as invincible, was being revealed as a machine optimized for a different kind of fight, one ill-suited to the industrialized, attritional air war the Allies now dominated. By December 1944, the captured aircraft evaluation program at Wright Field had logged more flight hours on enemy planes than any intelligence effort in aviation history. Ross's office overflowed with flight logs, performance graphs, and comparative assessments that collectively painted a definitive portrait of Luftwaffe capabilities and constraints. The FW-190, once mythologized as the apex of fighter design, now stood exposed through systematic American testing as a masterful but flawed weapon, a triumph of tactical brilliance constrained by its own engineering compromises. Fundamental strategic miscalculations within German aviation doctrine became starkly evident. The flow of intelligence surged dramatically after the Luftwaffe's disastrous New Year's Day offensive, Operation Bodenplatte. German losses exceeded 400 aircraft, many crash-landing largely intact, allowing Allied recovery crews to restore them for evaluation. Soon, Wright Field's hangars contained the most extensive assembly of captured enemy aircraft outside Germany itself, granting analysts unparalleled access to compare designs across numerous variants and production runs. Colonel Harvey Dorney, head of the Captured Aircraft Testing Division, authorized continuous, round-the-clock evaluation flights. As the European conflict neared its climax, American test pilots rotated systematically through various German machines, recording precise data on handling, control, and performance characteristics that frontline intelligence had only speculated about from incomplete battle reports. The FW-190D9, Messerschmitt Bf-109G, and Junkers Ju-88 night fighter all underwent methodical comparisons against American fighters under tightly controlled test conditions that stripped away the chaos and subjectivity of real combat. The results confounded both German propaganda and Allied expectations. While the FW-190 displayed strong performance below 28,000 feet, its superiority evaporated at higher altitudes, precisely where the strategic bombing campaign was fought. The BMW and Jumo engines that powered various German fighters offered robust power at low and medium levels but lost significant efficiency in the thinner air where B-17 and B-24 bombers operated. In contrast, American P-47 Thunderbolts and P-51 Mustangs retained outstanding performance well into the upper atmosphere, where the decisive aerial engagements took place. Ross meticulously documented these findings with the analytical precision of a scientist, converting anecdotal combat impressions into measurable tactical intelligence. His reports confirmed that the FW-190's famed roll advantage disappeared entirely above 325 miles per hour. At those speeds, American fighters maintained smooth, predictable control while the German aircraft controlled stiffness-turn precision maneuvers into physical struggles. The tactical consequences were profound. Luftwaffe pilots trained to rely on rapid roll reversals, and diving passes found those techniques neutralized in the high-speed domain that U.S. pilots could deliberately impose through superior aircraft design. Engineering analyses revealed the structural trade-offs underlying these behaviors. The FW-190's pushrod aileron system, optimized for crisp response at low speeds, produced dangerous flutter under high-G conditions, effectively shrinking its usable combat envelope at precisely the moments where control authority mattered most. Likewise, the wing's torsional flexibility, intended to enhance roll rate, introduced tip-stall tendencies that required constant vigilance to avoid. These flaws were not oversights or production defects, but deliberate design choices reflecting German assumptions about air combat. Short, decisive engagements favoring elite, highly skilled pilots. Captain Ray White's comparative flights against captured Soviet aircraft provided a revealing contrast. A Lavishkin La-5, obtained through liaison channels, routinely outturned the FW-190 and sustained dogfights despite being slower, rougher built, and less sophisticated mechanically. Soviet design philosophy prioritized durable, forgiving aircraft that enabled average pilots to excel in close combat. This approach exploited weaknesses in German engineering logic that Western evaluators were only beginning to appreciate. The tactical doctrine that emerged from these discoveries reshaped Allied fighter strategy. New engagement procedures were drafted not from combat anecdotes but from controlled flight testing of the enemy's own machines. P-47 units were instructed to engage the FW-190 at high altitude and high speed, where the Thunderbolt's superior power retention and rugged A-frame gave overwhelming advantages. P-51 pilots developed disciplined maneuver tactics designed to exploit the German fighters' stiffening controls and slow trim responses at altitude. Perhaps the most striking revelation was psychological rather than mechanical. Luftwaffe training had produced masterful pilots capable of compensating for their aircraft's inherent limitations, but this expertise disguised structural flaws that well-engineered aircraft should not require their pilots to overcome. When American pilots flew the same German planes, they immediately recognized features the Germans had accepted as normal as clear design inefficiencies. The implications stretched far beyond technical comparisons. Germany's aviation industry had pursued tactical brilliance within the severe resource and production limits imposed by total war. The United States, by contrast, was developing aircraft as extensions of its industrial and strategic strength, machines engineered for reliability, efficiency, and pilot integration across all phases of flight. The contrast was not merely technological. It represented two opposing philosophies of warfare, one dependent on extraordinary skill to extract performance, the other designed to make superior performance accessible to every well-trained pilot. Mechanical performance alone in the context of modern warfare. As Allied forces advanced into the heart of Germany and the Luftwaffe collapsed under the weight of overwhelming industrial superiority, Ross's exhaustive documentation of captured enemy aircraft exposed the ultimate failure of technological mystique detached from strategic reality. The FW-190's formidable on-paper capabilities concealed deep-seated systemic weaknesses that American engineering, production scale, and design philosophy were uniquely equipped to exploit. German mastery of precision manufacturing and tactical innovation could not offset the fatal misjudgment of what kind of air war industrial democracies were prepared to wage. The captured aircraft program's greatest revelation, therefore, was not mechanical but philosophical. German aviation had produced fighters that demanded extraordinary pilots to achieve peak performance, while American designers were building aircraft that enabled ordinary pilots to achieve extraordinary results through ergonomic design and systemic integration. This divergence defined not only the outcome of World War II's air campaigns, but also foreshadowed the evolution of aviation into the jet age emerging from wartime innovation. By spring 1945, as Nazi Germany disintegrated, the once feared FW-190 stood exposed as a symbol of brilliant tactical engineering constrained by strategic blindness, a technological triumph undone by its creator's failure to understand the industrial nature of modern conflict. On September 23, 1946, Lieutenant Charles Ross laid his pen beside the final page of the performance test of FW-190D9 FE-121, concluding 15 months of rigorous analysis that had demystified Germany's most vaunted fighter. The title on the report was dry and clinical, yet the document itself represented something far greater, the definitive technical autopsy of Nazi Germany's aerial ambition. Outside his Wright Field office, the Ohio landscape glowed with autumn's calm gold, a peaceful contrast to the transformative insights resting on his desk. 4 months after Germany's surrender, the captured aircraft program shifted from urgent wartime necessity to historical record. Ross's final report would soon rest among thousands of technical evaluations in sealed archives, its immediate value diminished by victory, but its scientific significance enduring. The American methodical approach to understanding enemy design had yielded not just tactical knowledge but profound insights into the connection between engineering philosophy and strategic success, insights that would guide aerospace development for decades to come. Colonel Harvey Dorney walked the aisles of Wright Field's cavernous hangars, now filled with the most extensive collection of German aircraft outside the defeated Reich itself. Rows of once-feared fighters, bombers, and prototypes stood silent, objects of study rather than symbols of terror. The FW-190D9, once a scourge of Allied formations, had been reduced to a case study in design compromise. Its once legendary performance now carefully dissected into charts, equations, and engineering lessons. The calm of peacetime offered reflection where wartime urgency had not. American test pilots had approached these captured machines with scientific discipline, uncovering truths that propaganda had long obscured. Beneath the legend of invincibility lay a record of remarkable engineering bounded by flawed strategic thinking. German aircraft represented excellence within narrow tactical contexts, limited by economic strain and philosophical rigidity. In contrast, American engineering thrived on adaptability, building aircraft that married pilot effectiveness with industrial feasibility. Captain Ray White, now assigned to experimental jet trials at Muroc Field, often reflected on the greater meaning of 3 years spent flying enemy aircraft. The difference, he concluded, was one of philosophy as much as technology. Where the Luftwaffe demanded prodigious skill to unlock full performance, American aircraft were being designed to extend performance through thoughtful control harmonization and pilot-centered ergonomics. This reflected a broader national capacity to mass-produce competence rather than depend on a dwindling elite. The captured aircraft program's ultimate discovery was not found in speed curves or roll rate tables, but in its exposure of two opposing worldviews. German aviation prioritized short-term tactical supremacy within crushing strategic limits. American design, by contrast, evolved toward an integrated system, linking training, engineering, and mass production into a cohesive structure that provided enduring advantage. It was a philosophy of scalability and sustainability, not of brilliance constrained by fragility. And in that philosophical shift lay the blueprint for post-war aviation, an industry and doctrine that would dominate not merely the remainder of the 20th century, but the very definition of air power in the modern world. Tactical superiority in narrowly defined combat situations had been the hallmark of German aviation, yet as the evaluation program wound down, Freeman Field storage depots became the final resting place for most captured aircraft. What had once been active intelligence assets were now transformed into static exhibits for technical study and historical preservation. The FW-190 variants that had undergone exhaustive analysis joined hundreds of other enemy designs, lined in orderly rows beneath vast hangars. Their wartime urgency had faded, but their educational worth endured, offering invaluable lessons for future generations of engineers and military strategists who would confront new forms of warfare requiring the same disciplined, methodical understanding. The institutional knowledge gained from these systematic evaluations extended well beyond individual flight characteristics. It fostered a comprehensive awareness of how technology intertwined with training, doctrine, and industrial organization to produce true strategic advantage. American pilots and engineers had learned that superior weapons alone were meaningless without integration into a broader system capable of sustaining effectiveness through prolonged conflict. The German model, producing highly specialized machines that demanded elite pilots, had proven vulnerable to the American method of fielding larger numbers of durable, easy-to-fly aircraft operated by well-trained, competent crews. Ross's final technical submissions entered classified archives destined to shape the next era of aviation. His data on German design strengths and vulnerabilities became the groundwork for an engineering philosophy that valued pilot assistance over pilot challenge, systematic efficiency over momentary brilliance, and industrial scalability over handcrafted superiority. These guiding principles would carry U.S. aviation confidently into the Cold War, where its adversary, ironically, would draw heavily on the same captured German research that had filled the hangars at Freeman Field. With wartime urgency replaced by reflective analysis, a broader understanding of the captured aircraft program's achievements emerged. The effort had done far more than identify tactical strengths or weaknesses. It had exposed a fallacy of technological mystique divorced from strategic realism. It demonstrated that even extraordinary engineering could be undermined by flawed assumptions, and that objective, methodical evaluation could pierce through propaganda to reveal a weapon system's true nature. The lessons extended far beyond aviation. They illuminated a fundamental truth about the industrial age, that democratic societies, through discipline, education, and scalable production, could outperform authoritarian systems obsessed with technical elitism. By late 1946, most captured aircraft had been shipped to museums or long-term storage, their engines silent but their significance preserved. The once dreaded FW-190, which had embodied German technological prestige, now stood as a monument to systematic American inquiry, proof that disciplined analysis could turn enemy legend into data and myth into measurable understanding. Ultimately, the difference between German and American approaches had never been limited to machinery. It reflected competing ideologies about the bond between human capability and mechanical design. Germany had built for brilliance, machines that demanded mastery. America had built for effectiveness, machines that multiplied it. The insight earned from 3 years of rigorous enemy aircraft testing became the intellectual foundation of post-war aviation policy, guiding American innovation as it faced new technological and geopolitical challenges. The legacy of dismantling the Luftwaffe's mystique endured, ensuring that even as the captured fighters faded into museum relics, their lessons continued to shape the philosophy of air power in the modern world.